Okay, welcome to today's video everyone. So in today's video we'll be looking at question 8b from the 2001 HSC exam. And the question is quite lengthy. There's 4 parts to it, so in this video I'll do part 1 and 2, and in the next video I'll do part 3 and 4. Okay, so let's have a look at part 1. Explain why for alpha greater than 0, that the integral from 0 to 1 of x to the power alpha times e to the power x dx is strictly less than 3 over alpha plus 1, and you may assume that e is less than 3. Part 2, show by induction that for n equals 0, 1, 2, and all positive integers, that there exists integers a sub n and b sub n, such that the integral from 0 to 1 of x to the power n times e to the x dx is equal to a sub n plus b sub n times e. And it's important to just remember that throughout this question, part 2, a sub n and b sub n are just some integers. Okay, so let's start off by having a look at part 1. Okay, so what do we want? We want to prove that the integral from 0 to 1 of x to the power alpha times e to the x dx is less than 3 over alpha plus 1. And what are we given? We're given that alpha was greater than 0, and we're told that we can assume that e was less than 3. Okay. So if you have a look at this integral here, this is a product of two functions, and so this suggests that we use integration by parts. Okay, now, with integration by parts, we need to choose what our u is and what our v dash is. Now, if you note that here we want to get alpha plus 1 in the denominator of a fraction, this might suggest that we integrate this function here, so that we'll get x to the alpha plus 1 over alpha plus 1. So if we want to integrate this, this is going to be our v dash. So v dash equals x to the alpha, and when we integrate it, that'll mean v equals x to the alpha plus 1 over alpha plus 1. Okay? And what about our u? Well, if v dash is x to the alpha, that means u is going to be e to the x. So u equals e to the x, and when we differentiate e to the x, that's simply e to the x. So u dash is equal to e to the x. So now we can apply our formula for integration by parts. So this integral this is equal to u times v and this is evaluated between 0 and 1, because these are our limits, minus the integral of between 0 and 1, so the integral of u dash, which is e to the x, times v. So u dash times v dx. Okay, so this was just the integration by parts formula. Okay, so let's go ahead and evaluate this part here. So when we substitute 1 in, we're going to get e to the power 1, so that's just e. So we're going to have e times 1 to the power of alpha plus 1. Well, 1 to the power of alpha plus 1 is going to be 1, because 1 to any power is 1. And then over alpha plus 1. So we're going to have e times 1 over alpha plus 1, which is e over alpha plus 1, minus, when we substitute 0 into here, this will become 0 to the power of alpha plus 1, which will become 0, and so the whole term is going to be 0. So this is going to be minus 0. Okay, and then minus this integral. Okay, so whenever you do these questions, you should always keep in mind what you're trying to prove. We're trying to prove that this is less than 3 over alpha plus 1. And if we look here, we have e over alpha plus 1. Now we have an alpha plus 1 in the denominator, which is what we want to have up here. And we also note that the question told us that we may assume e is less than 3. Now questions, they don't give you information for nothing. So we're going to have to somehow use this. So we can say since e is less than 3. If we divide both sides of the inequality by the same thing, that's not going to change the inequality. So we can say, therefore, e over alpha plus 1 is less than 3 over alpha plus 1. Okay? And so now we can say that this whole thing here, going to have, well, the integral from 0 to 1 of x to the alpha e to the x dx. Now it's equal to this, but because of what we've just shown here, it's now less than 3 over alpha plus 1 minus 0, which is nothing, minus the integral between 0 and 1 of e to the x times x to the alpha plus 1 over alpha plus 1 dx. Okay, so now we're pretty close to what we need to get. We need to get less than 3 over alpha plus 1. Here we have less than 3 over alpha plus 1 minus this bit here. So what we want to show, this is what we want to show. We want this now to be less than 3 over alpha plus 1. This is what we want. Okay, we want this bit. But how can we get to that? Well, if we're taking away something here, if this bit's positive, then we're taking away a positive value, which means that this expression here should be less than this. So if we're somehow able to prove that this integral, without the minus sign, this just the integral, if we're able to show that it's positive, then that means we'll be taking away a positive value from 3 over alpha plus 1, and so therefore this bit here will be less than 3 over alpha plus 1. So our aim now is to show that this is greater than 0. So let's just write that down. Our aim, we want to show that this is greater than 0. Okay? Alright. Now, how do we show that this is 0? Well, when we have inequalities, not inequalities, when we have integrals, what does an integral represent? Well, it represents the area bounded by the curve and the x-axis, because in this case it's dx, so it's going to be the area underneath the curve and above the x-axis. Now we want to show that this area is greater than 0. Now we're not required to actually draw this curve here, x e to the x times x to the alpha plus 1. Well, we don't really know what that's going to be because we don't know what alpha is. We just know that it's some constant greater than 0. Okay, so how are we going to do this? Well, let's have a look at this interval. We know that e to the x is greater than 0. Well, this is greater than 0 for all x, so it's definitely greater than 0 over this interval. So e to the x is greater than 0 for x between 0 and 1. Okay, so this is just another way of writing x is between 0 and 1. So in this interval, e to the x is greater than 0. And we know that x to the alpha plus 1, x to any power, whether it's an odd power, even power, fractional power, negative power, x to the anything is going to be greater than 0 for x in this same interval. And we only need to consider this interval because that's what we're working on. That's where this integral is being evaluated on. Just this interval here, this one. So since these two are both greater than 0 over this interval, then this means that we can say that their product is greater than 0 for x between 0 and 1. Okay? And now, if it's greater than 0, dividing by a constant, such as alpha plus 1, is not going to change the sign. So we can say that this here is greater than 0. Okay, now, if this function is greater than 0, what does it mean really? It means that it's above the x-axis over this interval. So if it's above the x-axis, the area underneath it is going to be positive. So we can say that this now means that the integral from 0 to 1 of e to the x times x to the alpha plus 1 over alpha plus 1 dx is greater than 0. Okay, and we've shown what we need to show. We've shown this aim. And so therefore, we now have what we want. We have this want of ours. Therefore, we can say that this integral is less than 3 over alpha plus 1. Okay? We've proven what we want. Okay, let's have a look at part 2 of the question. Now, part 2 says, show by induction that there are some integers. We don't know what the integers are. We don't necessarily know what they are, but we need to show that there are some integers, a sub n and b sub n, that satisfy that expression there. So, part 2, let's just write down what we want to show. X to the n, e to the x dx is equal to a sub n plus b sub n times e. Alright. We want to show this as well for n equals 0, 1, 2, all positive integers and 0. And we're showing that this a sub n and b sub n are integers. B sub n are integers. Alright. So I always like to write down what we need to show and all the information that we have before I start the question. Okay. So we start off by proving the smallest case possible for n, which is 0. So when n is equal to 0, what's the left-hand side? Well, the left-hand side is going to be the integral of 0 to 1, between 0 and 1, of x to the power 0, which is 1. So the integral of 1 times e to the x, so the integral of e to the x dx. Okay, integral of e to the x is simply e to the x. And it's evaluated between 0 and 1. When we substitute these limits in, these bounds, we're going to get e minus e to the 0, which is 1. And let me write it like this, minus 1 plus e. Okay, now I can say that this is equal to a sub 0 plus b sub 0 times e, where a sub 0 equals negative 1, and b sub 0 equals 1. Okay, and so this is now equal to the right-hand side. And therefore, it's true for n equals 1, or n equals 0. N equals 0. Remember, that's what we proved it for. Okay, so that's good. We've proven our base case. Now we need to make our assumption. Okay, so assume n equals k is true. So if we're assuming n equals k is true, that means we're assuming this statement. E to the x dx, well, that shouldn't be n, that should be a k. X to the k e to the x dx is equal to a sub k plus b sub k times e, where a sub k and b sub k are integers. Okay, this is very important that they're integers. This is pretty much what makes this assumption what we want. So we need to show that there exist integers. So our assumption is that these integers do exist. Okay. Now, what do we want to prove? We want to prove n equals k plus 1. Okay, what's the n equals k plus 1 statement? Well, here it is. X to the k plus 1, e to the x dx equals b sub k plus 1 times e. So we want to show that there are some numbers, a sub k plus 1 and b sub k plus 1, that are integers. That's all we want to show, that there are some integers here that exists for this integral. Okay, so once again we have the product of functions here. So we have our left-hand side. Let's just write it again. Our left-hand side is the integral from 0 to 1 of x to the k plus 1 e to the x dx. And we want to probably be using integration by parts because we have this product of functions. Okay, so what do we choose as our u and what do we choose as our v dash? Well, if we have x to the k plus 1, we want to try and involve this here. So we want to reduce this x to the k plus 1 to just x to the k. So this would probably suggest that we select u as x to the k plus 1, which means u dash would be k plus 1 times x to the k. And that means v dash is going to be e to the x, and so v is e to the x. Okay, so our left-hand side is going to be this integral, which is going to be u times v, x to the k plus 1 times e to the x, evaluated between 0 and 1, minus the integral of u dash times v. Okay. Alright, let's evaluate this bit here. When we substitute 1 in, we're going to get 1 to the k plus 1, which is 1, times e to the power 1, which is e. So 1 times e is e, and here we're going to get 0 times 1, which is going to be 0. So e minus 0. Now k plus 1 is a constant, so I can take it outside the integral. And this is what I get. Okay? But from our assumption, just here, we just assumed that this integral, which is what we have here, was equal to a sub k plus b sub k times e, where a sub k and b sub k are integers. So this is going to be e minus 0, we don't need to write, minus k plus 1 times a sub k plus b sub k e, where a sub k and b sub k were some integers. Right? This is our assumption. This was the main part of our assumption. Okay, now let's write it by grouping the e's together and the non-e's, if you might, together. Okay, so when we have the non-e parts, this is what we're going to get. And our e parts are going to be plus, let's see, we're going to have 1 minus b sub k times k plus 1 times e. So you can just check that by yourself. But what we're doing is we're collecting all the terms with e and all the terms without e. Okay, now this is going to be a sub k plus 1 plus b sub k plus 1 times e, where a sub k plus 1 is equal to this expression, minus into k plus 1 times a sub k, and b into k plus 1, or b sub k plus 1 is equal to 1 minus b sub k into k plus 1. Okay, let's slide that up. Okay, so this is what we have. Now, how do we know that these are integers? Well, we know that k is an integer because k is can only take the values that n can take. So, since k is an integer, now obviously 1's an integer, that's too explicit to even have to write down. It's obvious that 1's an integer, and we've assumed that a sub k is an integer, right? I've written it here, but in our assumption, we said that a sub k and b sub k were integers. So since k is an integer, and a sub k is an integer, this means that which is a sub k plus 1, which is equal to negative k plus 1 a sub k, is also an integer. Right? When we multiply integers, and when we add integers, and when we subtract integers, it's always going to give us an integer. So this little property here is actually called closure under certain operations. So the field of integers is, or the class of integers, whatever you want to call it, it's closed under addition, subtraction, and multiplication, which just means that if you multiply two integers, add two integers, or subtract two integers, you're going to get two integers. Okay, and similarly, as you can see, b sub k is an integer, and so we have that b sub k plus 1, which equals 1 minus b sub k times k plus 1 is an integer. Okay, and so therefore it's true for n equals k plus 1 if n equals k is true. Alright? And then you can make your statement saying, since it's true for n equals 0 and true for n equals k plus 1 if n equals k, then it's true for all integers 0, 1, 2, 3, and so on. Now I'm not going to write that in this video, but I'm sure you know the statement to make. Okay, so that was, once again, just part 1 and 2 of the 2001 question 8b HSC exam. Okay, and the next video will be the next two parts. Now, as you can see, it's quite a long process. This video is longer than what you should take in an exam because I'm trying to explain everything step by step and clearly, but it's definitely a long question and it is definitely targeted at the really higher students, but by no means you should not attempt it. You should definitely attempt these questions. There are marks that you can pick up. Okay, thanks for watching.